AudioJungle.
Welcome to SCIstorm, and this is the second video of our quantum computing video series. In the last chapter, we covered the fundamentals of quantum computing, such as qubits, superposition, and entanglement. Key quantum algorithms, future applications, and historical evolution were all covered. This chapter lays the groundwork for learning more about the fascinating realm of quantum computing. In this chapter, we will look into quantum algorithms. Quantum algorithms. Introduction to quantum algorithms. In this chapter, we will explore the fascinating world of quantum algorithms and their importance in unlocking the full potential of quantum computing. Quantum algorithms are at the core of what makes quantum computing so powerful. They leverage the unique properties of quantum mechanics to perform specific computational tasks faster than classical algorithms. By understanding quantum algorithms, we can gain insights into the remarkable speed-up that quantum computing offers over classical computation. Quantum search algorithms. One of the first quantum algorithms we'll explore is Grover's algorithm, a quantum search algorithm. Grover's algorithm is designed to efficiently find a target item in an unsorted database. By leveraging quantum superposition and interference, Grover's algorithm can achieve quadratic speedup compared to classical search algorithms. We will examine the working principles of Grover's algorithm and see how it has practical applications in searching databases and solving optimization problems. Factoring with Shor's algorithm. Shor's algorithm is a groundbreaking quantum algorithm that has significant implications for cryptography and security. It can factor large numbers exponentially faster than classical algorithms. We'll dive into the step-by-step process of Shor's algorithm, including quantum modular exponentiation and the quantum Fourier transform. Understanding Shor's algorithm will highlight the potential threat it poses to classical cryptographic systems and its importance in the development of quantum-safe cryptography. Quantum simulation algorithms. Quantum simulation algorithms play a crucial role in understanding and simulating complex quantum systems that are challenging for classical computers. We will explore how quantum computers can efficiently simulate quantum materials, chemical reactions, and other quantum phenomena. The advantages of quantum simulation over classical simulation will be discussed, and we'll see how quantum simulation opens up new possibilities in the fields of physics and chemistry. Quantum machine learning algorithms. Quantum machine learning is an exciting area that aims to leverage quantum properties to enhance machine learning tasks. We'll explore how quantum computers can potentially accelerate pattern recognition, optimization, and other machine learning tasks. Understanding quantum machine learning algorithms will provide insights into the potential synergy between quantum computing and classical machine learning methods. Quantum approximation optimization algorithms, QAOA. Quantum approximation optimization algorithms, QAOA, are designed to tackle combinatorial optimization problems. We'll delve into how QAOA uses quantum annealing to find near-optimal solutions to difficult optimization problems. Practical applications of QAOA in fields like logistics, finance, and operations research will be discussed, showcasing the potential impact of quantum computing in real-world optimization tasks. Quantum error correction. One of the major challenges in quantum computing is dealing with errors caused by noise and decoherence. In this section, we'll address the critical need for quantum error correction. We'll explain quantum error correction codes, such as the surface code and stabilizer codes, which are essential for preserving the delicate quantum states of qubits and enabling reliable quantum computations. Quantum circuit synthesis. Quantum circuit synthesis involves transforming abstract quantum algorithms into physical quantum circuits that can be implemented on quantum hardware. We'll explore the optimization techniques used to minimize the number of gates and reduce circuit depth for more efficient quantum computation. Understanding quantum circuit synthesis will provide insights into the practical implementation of quantum algorithms on existing quantum computing platforms. Quantum algorithms and quantum hardware. The interplay between quantum algorithms and the physical constraints of quantum hardware is crucial for successful quantum computation. We'll discuss how qubit connectivity, gate fidelity, and decoherence impact algorithm design and execution. Tailoring quantum algorithms to specific quantum computing platforms becomes essential to achieve practical results. By exploring these quantum algorithms and their connections to quantum hardware, you'll gain a deeper understanding of the capabilities and limitations of quantum computing in various applications. These algorithms represent the frontier of quantum computing, and understanding their principles will shed light on the possibilities that lie ahead in this rapidly evolving field. In this chapter, we looked at sophisticated quantum algorithms that outperform traditional ones. These include the quantum simulation algorithms, the Shor factoring method, and the Grover search algorithm. Algorithms for quantum machine learning and optimization were also covered. Realizing the promise of quantum computing requires an understanding of these algorithms. In the next chapter, we'll look into quantum hardware, which is the physical implementation of quantum computing. We will become familiar with several qubit technologies, such as trapped ions and superconducting qubits, and comprehend their advantages and disadvantages. The chapter will also go over important elements of developing quantum computers, such as error rates and qubit stability. By the conclusion, you will have a general understanding of the state of quantum hardware today and the continuing initiatives to make quantum computing usable. Join us on SCIstorm as we continue to dig into the mysteries of quantum computing and other fascinating topics for more engrossing material. To keep up with the newest videos, and become a part of our expanding community, subscribe to our channel. Don't pass up the chance to learn more and be motivated by the most recent developments in science and technology. Until the next video, take care.